meeting right now. So hello everyone. Thank you for joining the CPOS seminar series this week. I am the speaker this week. So to introduce myself, my name is Tung Nguyen-Dang. My passport name is Nguyen. That's the reason why you see my my invitations with the Nguyen name, but my pen name is Nguyen-Dang. I graduated from École Polytechnique Fédérale de Lausanne with a PhD. And before that, I did my bachelor in Polytechnique, École Polytechnique in France. So I spent most of the time in Europe, and I worked for a year in a company named Saint-Gobain, the glass making company, before joining UCSB. In UCSB, I'm working in the group of Professor Nguyen in the Center for Polymers and Organic Solids, and I have an affiliation with the CNSI through the group of Professor John Wissel. So today, I would like to share with you my recent results on the microfabrication of organic semiconductors for electronic and optoelectronic applications. Basically, today I will make the case for the need of coupling processability and functionalities in organic semiconductors. So let me start with introducing a case of a case that the interplay between the functionalities and processabilities has resulted in one of the biggest breakthrough in technologies in the recent years. So it's the optical fiber. As you know, the first glass has been invented by the Babylonian people like 3,000 years ago, like 4,000 years ago. And the physics of internal total reflections has been worked out for quite a few times in 1500 by Snell and Descartes, two pioneers at this time. But there's a need for a waveguide only when the laser was invented in 1955. And in 1965, that is where the first waveguide, low-loss fiber waveguide, has been demonstrated by Dr. Kao, who was awarded the Nobel Prize in 2009 for this invention. So he made the case that optical fiber, so silica fiber, is not restricted by the fundamental physics dispersions, but only by the impurity. So the silicon is, if the silicon is pure enough, we will have the very good waveguide. So as you can see here, even though the physics and the materials exist for a very long time, the application happens only when we have a need. And then with the demonstrations of the first low-loss fiber waveguide in 1965, people went on to create a very high throughput fabrication techniques called the thermal drawing techniques. And these techniques combined with the invention of Charles Kao that created the optical fiber fields that we know today that allow us actually to have the internet, basically. Just want to introduce the thermal drawing techniques. So you can see on my hand here is the pieces of polymer. And the thermal drawing techniques consist of heating the polymers precisely at a certain location and then change the viscosity of the materials. So it started to neck down under our weight, and then which could be pulled from the other end, and the constant pulling of the other end of the fiber of the pieces create a neck down region so that the pieces of polymers become a fiber. These pieces of polymer called a preform, and that is the fiber. So basically, by controlling the techniques, we can generate a very sufficient amount of optical fiber at very cheap price. And I'm sure that the cheap price features that make the optical fiber so popular. Of course, the rest is history. Now I just want to go on and really discuss on the functionalities and the processability. Well, the functionalities of silica is that it's very transparent, and it's very transparent at certain wavelengths that is important. For example, as you can see here on the left-hand side, we have the attenuations of the optical fiber versus wavelength, and things called the third windows. That's the wavelength of 1500 to 1600. The attenuation or the loss of the optical fiber is extremely small. It's basically 0.2 decibel per kilometer or 5.5% per kilometer. It's really transparent. And this wavelength corresponding to a kind of fiber applications and of a laser that allows this wavelength and this optical fiber to be used in optical communication. So yes, we have the materials that's really good for functionalities. Now, in terms of processability, that is the jackpot of silica. So silica, when you increase the temperature, the viscosity of silica decrease. But at certain temperature, at 1,200 degree up to 1,600 degree, the change in viscosity is quite small. Note that this is a log scale. So when you process a polymer with such a constant viscosity, it's easier for the tolerance for error is really high. So that makes the silica can be used in thermal drawing techniques in a very scalable way, and that allows to make a very, very cost-efficient devices. And the functionalities and the processabilities are the two keys for silica to be successful in the application optical fibers. Now, if we think about organic semiconductors, in terms of functionalities, it's way beyond silica. Optical fibers, organic semiconductors can be conjugated polymers, conjugated polyelectrolytes, or small molecules. And the electrical conductivity, for example, of the organic semiconductor can be tuned from very high, such as close to metals, into quite low, like an insulator. The optical absorptions can also be tuned. I showed you here basically the work of CPOS members, Dr. Ji-Won Lee. So he synthesized a series of materials. As you can see, that they look very similar to each other. The difference is the side chain. But this small difference can be used to tune the absorptions kind of very finely from 800, the peak from 800 to the near infrared of around 1,100 nanometer. So really, the functionalities of organic semiconductor is really well beyond that of silica, and it can be easily tuned by chemical designs or chemical synthesis. The processability of organic semiconductor is also very good, but it's mostly related to solution processing. We have here the evaporations of small molecules, but that is an exception. Most of organic semiconductors are polymers, like conjugated polymers or conjugated polyelectrolyte were fabricated, are fabricated with solution processing techniques, spin coating, inkjet, printing, drop casting, and double blading. These are the schematics of these techniques. And as you can see, these techniques are really good to make thin film 2D structure. If we think of future generations of optoelectronics and electronics that require higher complexity, like in 3D, well, I just give an example of the brain, because for me, the brain is the highest form of complexity that we can get. And of course, that is the goal of researchers to go towards this kind of goal, to have this kind of complexity. And with the current state of the art, organic semiconductor, in my opinion, cannot reach this kind of complexity. Now, if I want to show the breakthrough relevance map, actually it's the product of functionalities and processability. You have here like a 2x2 matrix. When on the x-axis you have the processability, and the y-axis you have the functionalities, and the area here is basically the product of these two axes. at the low quadrants, we have quasi-crystal. So that is the fascinating materials that have no use yet, and it's very hard to make. So so that is just like a wonders of nature. And this silicon here, on the other hand, has a lot of functionalities. It can be used as waveguide in infrared. It can be used as semiconductors in photovoltaics, and it can be fabricated by many ways. It's really one of the materials that define our time, the silicon edge. So it's really huge on this quadrant. I put silica because I just showed you the optical fiber. The functionality is not much. It's just very transparent, but it can be produced in a very scalable way and in a very complex way. So it's actually quite high, and it's moving towards this quadrant. Now, organic semiconductors, in my opinion, and that is actually my opinion alone, that is this really high functionality. It ranks really high in functionality skill, but in terms of processability, there are a lot of rooms to work with. So the idea is we can push the organic semiconductors from this quadrant to this quadrant. So they started to replace silicon in some key applications in electronics or in optoelectronics. So that is the big motivations of my work. And actually, it's really a timely motivation, because many new applications require mechanical properties and form factors that silicon wafer-based technology cannot address. For example, if you go to the hospital right now, you can see that the operation, the surgery, and it's not done by opening a human body, but just by digging a very small hole and pass through robotics arms. So these arms actually do the work of the surgeons, and the surgeons just control the arm through monitors and at distance. Now you think that this kind of technique is cool and is really advanced, but it actually the surgeons here don't feel anything. They just rely on the hands. And I don't know if you try to move something without feeling anything. It's very tough. And actually, that's the reason why they are paid really well. Now, if we can include some kind of haptic sensation into these robotics arms, that solves a lot of problems, and that's reduced the cost of these techniques, and it increased the precision of the surgery. In order to have some haptic sensation, you need something soft, flexible, stretchable, and that would not be silicon. That would be the promising land for organic semiconductors. And that is one example. Other examples included virtual reality, exoskeleton, robotics, also implantable electronics. And these are really good opportunities to do research in organic semiconductors in terms of processing and to increase the processability of the organic semiconductor. Now, this coupling of functionality and processability is actually happening at the moment. It's really a fertile and consequential research domain. These are the three groups that have come here and given talk. So I had the chance to read their work and discuss with them, and it's really a fascinating field where you can, from the chemical side, tune the chemical structures, then you test the mechanical properties, and then you refine these schemes in order to achieve the mechanical properties that you want. For example, Professor Nuscombe in University of Washington, she shows that by twisting the macromolecular differently, you can achieve a different stiffness of the materials. Or Professor May in Purdue University, he did a very cool job. He synthesized organic semiconductor by adding the amorphous chains right here to connect the organic semiconductor domain. So that he has the functionalities of organic semiconductor, but he has the processability of that amorphous chain, and usually that is an engineering material. In terms of fabrication techniques, we have here Professor Amartyan at North Carolina State University, and he has developed many cool fabrication techniques. Of course, Dr. Blading is something very interesting, but he started to print organic semiconductor in 3D. So that would result in a lot of breakthroughs, but also that would require a lot of fundamental understanding on the relationship between the functionalities and the processability, the structure and the functions of organic semiconductor. Now, for my part, actually, as you can see here, I arranged the field from nanometer up to meter or kilometer. So from nanoscale to micro scale up to the macro scale. The micro scale that deals with molecular design and chemical synthesis. And the words that you may hear sometimes is absorption. So these are the grounds where Professor Lu Kong or Bei is working on. On the other side, you have the device integrations that cover the range from like millimeters to meter or sometimes 100 micrometer. So that is the range where I show you that Professor Amartyan. Now in the middle here, there's a range that consists of device physics, cell assembly, and with properties such as viscosity. Viscosity cannot, it's very hard to define viscosity at nanoscale. The viscosity started to exhibit at the micro scale. And apparently that is also uncharted territory in organic semiconductor. Because device physics and cell assembly has been studied quite a lot, but there's a lot more room to work on. And that is also related to my PhD work. So that is my current research is dealing with the micro scale of organic semiconductor from fabrication to properties. So the highlight of my talk today will be, I just give you the introductions of the field. The second step, I will show you how they take advantage of one properties of organic semiconductor to invent a new OECT fabrication technique. And the third part could be a discussion on an idea of applying viscous flow engineering in organic semiconductor field. And after the conclusions, I hope that we will have some time to have a long discussion. So now first part of the talk is on organic semiconductor, organic electrochemical transistors and the new fabrication technique. I want to introduce the organic electro transistor to the audience. Organic electrochemical transistor on OECT for short. This three-terminal device consists of a source and drain and a gate, and a semiconductor, organic semiconductor, that links the source and the drain. And the whole system normally is put in an electrolyte with cations in red here and anions in blue right here in this schematics. So there's a current that goes from the source to drain generated by a voltage applying VT. And now if we apply a gate voltage, like positive gate voltage, we will have an accumulations of ions, like a migration of ions from the electrolyte to the semiconductor. And in this case, because it's the positive gate voltage, it could be the cation accumulations of the semiconductor. The anion will be accumulated, will accumulate at the gate. Now, the accumulation of ions into the film would result in some chemical reactions. And the chemical reactions would change the conductivity of the semiconductor materials. That is the working mechanism of this transistor. For example, in case of PEDOT-PSS, which is the very well-known organic semiconductor used in OECTs, with the migration of cations, there will be oxidize reactions that oxidize the PDOS from the conductive state to a non-conductive state. So basically, if now we trace the drain current as a function of the gate voltage, we can see that at lower gate voltage, so basically there is no migration of cations, the current will be very high because the PDOS PSS is still in the conductive state. Now, if we increase the VG, we can go to the range where the PDOS become very non-conductive. And basically, if we can increase further the VG, we started to suppress the ID completely. So the device will be in an off state. There is a figure of merit that is important in this graph, is the transconductance. So basically, it's the slope of the transfer characteristics, the slope of this curve. The steeper the slope, the higher the transconductance. So the higher the amplification factor that this transistor can provide. I want to note that this transistor works in an accumulation mode. I'm sorry, it's in depletion mode. That is the mistake here. Depletion mode meaning that is started when there's no gate voltage, it started at an on state. And when you apply a gate voltage, it's going to be the off state. And the other state is the accumulation mode, where you started at the 0. And when you turn on the V-gate, the device is on. Now, OECTs, because it relies on the migration of cations or ions in general, requires a really low voltage, and it also requires low power consumption. And because it can be seen as an ionic electronics transducer, because it transduces the ionic current of the electrolyte to the semiconductor to electronic currents that go through the semiconductor. So it is really it's really promising for bio applications. For example, I show you here on this slide the difference between the organic field effect transistor and organic electrochemical transistors. So the low voltage comes from the fact that in an OFET, you need to induce a strong dipole here to have a layer of conducting semiconductor. Whereas in an OECT, the conducting or non-conducting happen at the bulk level. So this requires low voltage and low power consumption. The ionic transduction properties has been used in applications such as brain recording. For example, here in this slide, and this is the EEG using two types of OECTs, and this is the in vivo brain recordings of a mouse. All this work is done in the Malia Ras group, and actually, if you want to know more, I would strongly recommend you to read the review paper of this group by Rifni and Malia Ras in 2018. Other features of OECTs would include flexible and stretchable because it can be made on organic. It's biocompatible and it's robust in air and humidity. Well, this robustness in air and humidity, in my opinion, does not really happen often with OFET. The OFET is quite sensitive with humidity and air, with oxygen, whereas OECD requires some certain amount of humidity to work in most of the case. And the thing with an OECD field is that at the moment, there's only two categories of fabrication OECD, to fabricated OECD, either very simple and rudimentary or very precise and complicated. And I want to note that the one who possess the capability of fabricate OECD very highly precise, actually have the right to kind of monopolize the field. In this case, Malia Ras and his students and postdocs. The simple and rudimentary methods consist of spin coating or drop casting of organic semiconductor in between two electrodes and using hand, say, to define the area channel, the area of the channel. The pros of this approach is they are easy and expensive, and it's good for proof of concept, but of course, it's not suitable for quantitative research. It's very difficult to reproduce, and is almost impossible for miniaturization as large-scale fabrication. The other side, because they evolve a lot of complicated fabrication techniques and clean room processes, this is very producible and really good for quantitative research, like accessing the properties of organic semiconductor, and also is allowed for miniaturization, as you can show here. And again, as I showed before, this work has been done in the Maliaras group, and since 2011, with this technique, they really dominated the field. The problem is that it requires a certain amount of investment in terms of know-how, in terms of equipment, facilities, in order to do this, to make this technique work. For example, we don't have here in UCSB the parallel C depositions that I know of, and it's quite expensive. So if you think of a field that want to expand, that is the high entrance barriers. So my motivations for this is actually to create a new fabrication techniques that addresses some difficulties that the field is facing. Have to yield a high performance OECT. It has to be suitable with the studying of organic semiconductor. Again, I'm sorry for these acronyms, it has not been defined. And it has to be compatible with miniaturizations. It needs to be, and that is the main motivation, widely available, simple, and inexpensive. The clean room facilities really relies on the understanding of inorganic materials most of the time. You can think of etching, for example, of silicons or some things like that, plasma etching. Now, if we can use the properties of organic semiconductor, like unique property of organic semiconductors that are different from the ones of inorganic semiconductor, we might find a way to have a shortcut in terms of fabrication process. At the same time, we provide a possible enhancement of organic semiconductor via chemical treatment. So that's what I mean. I proposed a new fabrication techniques. So on a substrate with the channel, with the source and drains already evaporated, we just keep an opening on the channel side, and then we spin coat the organic semiconductor. So at this point, instead of having another lithography process to define the channel and another etching process in order to really bombard the materials to remove the extra organic semiconductor, and then another step of killing, we just require a solvent treatment. So this step of solvent treatment would replace at least 2 other steps in terms of fabrication techniques that are currently available. The solvent treatment can also provide us an opportunity to enhance the performance of organic semiconductors, and that is unique to organic semiconductors, because if you dip silicon in any solvent, you either dissolve it or it doesn't change anything. So that this proposed fabrication process is a simple fabrication technique that provide enhanced performance. So in order to demonstrate these techniques, I selected the several materials that are relevant. First of all, for the photoresist that I show here, I chose the very common photoresist AZ4000 series. That is one of the most common photoresists that are available in all of the clean room. It's very easy to work with, and it's very inexpensive. So this material can be dissolved with polar solvents like NAP, acetone, or DMSO. For the OECT, I chose the most widely used, the PEDOT-PSS, because if it works with PEDOT-PSS, it can have a bigger impact in PEDOT-PSS. So I chose several dopants like ethylene glycol to enhance the conductivity of the PEDOT-PSS. I also choose the BBSA in order to to improve the film formings of the PEDOT-PSS, increase the viscosity. and I added a cross-linker GOPS in order to stabilize the BWSS in aqueous solution. So with these materials, I implemented the techniques. So basically, following the fabrication steps that showed on the previous slide, I could pattern BWSS in silicon in a very precise way. As you can see here, this work, I present this slide in 1 minute, but it doesn't take into account hours of optimizations, and I would like to thank Kelsey for helping me with that. On this picture, you can see the channel right here in between the two electrodes, and the distance, the channel width is increased from 20 microns, 40 microns, 80 microns, and 100 microns. And it can be very neat. It works also with plastic substrates. For example, thanks to the recommendation of Dr. Shantanu Biswas, I work with PEI substrates. And it's really interesting to see that we can put the gold on the silicon, and then we can treat, we can go through the whole fabrication steps without destroying the substrate, and then we just peel off the substrate, and then on this substrate there are BWSS patterned in the very same way as you pattern BWSS on silicon. In terms of performance of the BWSS, so I use in this slide I showed you how I characterize this the performance of BWSS by using the transfer characteristics. We can extract certain values, basically the threshold voltage and the conductance. And using impedance spectroscopy, we extract the capacitance of the film. So from these two values, we can extract the conductivity of the film. We can extract the home mobility. We can extract the charge carrier density, and we can extract the volumetric capacitance. So those are four figure grids that I use to evaluate my devices. As I mentioned earlier, with the AZ4000 photoresist, we can use several solvents, and I choose 3 solvents, also well known, and DMSO is biocompatible. And it showed that by using different solvents, we changed a little bit the mobility and the volumetric capacity of BWSS. And this value is, for example, there's an inverse proportional between the capacitance and the mobility. Basically, with DMSO, we have the highest volumetric capacitance, but we have the highest mobility with acetone treatment, whereas the volumetric capacitance of the acetone treatment is the smallest. Overall, these values are quite stable. It's not like an order of magnitude difference. And the performance of the device been matched by the products of the mobility with the volumetric capacitance showed a very high performance of BWSS or OECTs. So this graph shows you the plot of mobility versus volumetric capacitance of several materials has been used in OECT. And these are the classic BWSS, but also there are like P3HT and PG2T, TT. Basically, we are in a higher quadrant, and the products of mu with C star is comparable or higher with than most of the materials, and comparable with high performance device by the Malia-Ras group. This is the Malia-Ras group. So to understand why we have this higher performance, so I would like to thank Samin to conduct the morphology characterization with GWAPs. So the blue curve here is my devices with GOPS. So basically, the characterizations of Shamin so that showed that GOPS has cross-linked the PWPSS, and he did also AFM characterizations, and he didn't see any big change in morphology of the PWPSS with different treatment. So we think, we hypothesize that the GOPS has cross-linked the PWPSS, and it makes it very difficult for the chemical treatment to alter the properties of the materials. So with GOPS, we can already define the performance of the PWPSS at the beginning, and then the fabrication technique would not alter this figure of merit. However, Shamin also showed very interesting result that without the GOPS, he showed that if we doped it with ethylene glycol, we have higher, show here, a higher conductivity compared with the pristine PWPSS. So that is the well-known fact. But now, if we doped it with ethylene glycol and we treat it with DMSO, we see different features. So basically, we may see a high enhanced in conductivity. So one of the experiments I will do next is actually using the PWPSS without GOPS in order to see that my fabrication techniques, when applied with these materials, may result in a wider range of figure of merit, say conductivity or volumetric capacitance. I apply this technique with CPK. It's the new conjugated polyelectrolytes that are synthesized by the CPOS, and here in this case by Luana. Alex Liu in our group has done a very good job of showing that this CPK can be an excellent active materials for OECT. So I used the materials provided by Luana and apply the techniques, and I can pattern the CPK either with a thin film or with very thick film. With thin film, we can have the very well-defined structure. With thick film, it's kind of difficult to remove some features. It also needs to optimize that some more work to be done. But overall, the OECT performance of CPK OECT with that new fabrication techniques is comparable with the drop casting techniques that done by Alex previously. So we show that it works in accumulation mode. So it's a good mode. It's not good. It's a different mode than PWPSS with a high on-off ratio and the device on at the low voltage. So basically, it works so well, and that shows that the new fabrication technique can work with different materials other than PWPSS. And in terms of application, I demonstrated the use of the OECT made with this new fabrication technique in chemical sensor. So basically, we measure the concentration of methylene blue in PBS. So the device consists of the source and drain and a gate divided into a two-compartment channel. So a well of the DMS, as you show here, and the electrolyte, we use methylene blue in PBS. So the fundamentals of this sensing, the working mechanism of this sensing is the follow. Here on this schematics, you have the immigration of ions into the film, and then you have the accumulations of anions into the gate. So in this configuration, we can deduce a simple ionic circuit consists of two capacitors. Basically, if you think about that, the gate voltage that apply from this part to this part will be divided in two interfaces. The gate and the electrolyte interface, and the semiconductor and the electrolyte interface. So if we apply the same gate voltage, but now we modify the voltage drops on this interface, then we modify the drop of voltage on this interface. So we modify the conductivity of the semiconductor. The level of change in the drop of voltage of the gate electrolyte interface depends on the reactions. In this case, the redox reactions of methylene blue, the higher the reaction rate, the higher drop of voltage we can record, and then it's the lower the conductivity that we have here, and the higher conductivity in PSS. And then we demonstrated, again, with help of Kelsey, 10 nanomolar sensitivity detections of methylene blue. On this part, I would like to thank sincerely a lot of people, because this is really new to me, everything in biology and chemical sensing. So I would like to thank Professor Ryo Siponaru, Brian, and also many people in the Fluxco group for helping me in discussing the projects and also for providing materials. In short, we demonstrated a chemical sensor with 10 nanomolar sensitivity using the OECT made with the new fabrication technique. The conclusion of this part is that we will do a little bit more on demonstration of local sensing, and then we will write a manuscript on that. I would like to add that with this electronics that already, I would like to attack the problem. I mean, I attack with more functionalities by providing, for example, capacitive tactile sensing that I had demonstrated in the past, but I didn't find the good electronics platform. OECT seems to me the good electronics platform. So like 10 minutes of my time, I would like to introduce the second part of the talk on the viscous engineering fabrication techniques and discussions on how to apply that on organic semiconductors. So basically, viscous engineering fabrication techniques are techniques that require the precise control of the viscosity of materials at different fabrication steps. For example, with micro embossing. So this can be controlled, the viscosity of the materials can be controlled by annealing, increase the temperature physically. So the viscosity will decrease, that you can allow to push a stamp on and then remove the stamp. By cooling it, the viscosity will reduce the viscosity will increase enormously, so there's will be no deformation. And now by removing the stamp, we will have the microfabrication, microstructures. The viscosity can be controlled also by chemical routes, for example, by resin curing. If you work with PSS, you know that you can pour PSS in liquid forms on the mold, on the stamp, and then you just cure it, create chemical ring, and then you change the viscosity. After curing, the viscosity is extremely high and there's no deformation. But there's another type of viscous flow engineering in fabrication techniques, and that requires a flow of liquid at very small. So you all know that when you have a draw small perturbations on a big pond or legs, actually the surface will be smoothened. In case of a small scale, like a very thin film, it will result in surface breakup. This is because of the surface tension effect. Basically, the liquid try to minimize the surface energy, and by minimizing the surface energy, it breaks into small droplets. This thing is called plateau Rayleigh instability. With the conditions is that it should be a very thin film. I mean, a highly aspect ratio, and the characteristic time of this deformation depends on the viscosity and on the surface tension. Basically, the higher the viscosity, the longer the time, and the lower the viscosity, the shorter the time, inversely with the viscosity. And it works with different length scale, and the time depends on the length scale also. So now, if we have the high viscous fluid, we can actually have a very high characteristic time. And then by that, we can measure the viscosity, or we can use this to control the flow of the materials for fabrication techniques. And during my PhD, I have out with the projects that using templated substrate to fabricate metal surface of chalcogenide glasses. The math I would not mention here due to the lack of time. So basically, we solved the Navier-Stokes equations with very specific boundary, by a pattern boundary, and we control the time and temperature relationship in order to make the wetting or the breakup happen at the precise positions that we chose. For example, in this schematics, I show you how a rod of water can maybe break up, or rod of the materials when you decrease the viscosity, and it started to break up into droplets. And the same thing happened if you evaporate a thin film of materials on top of a patterned substrate, and then you anneal it to reduce the viscosity. So basically, it started to break. And because you have certain patterns, it started to break into the places where you want to happen. If we control the processing techniques very well, we can have a very homogeneous structures. For example, I showed here the work done by a grad student. He really created a centimeter square of chalcogenide metal glasses. And then this called meta surface, because the particles, when they interact with each other, is similar like atoms interact with each other in materials. And that allows us to have tunable optical properties in photonics, and from that in biosensing. So for example, in these simulations, I show you here two different types of lattice. Here we have the triangular lattice, and here we have the square lattice. And then we have the same size of materials. So by controlling the lattice, we can control the interactions between the particle, and then we can enhance absorption at a very specific wavelength. For example, here you have extremely high absorptions with the square lattice. So my friend also study with a lot of size and shapes, and he shows a lot of cool techniques, resonances. And he shows also a lot of breakups in different patterns, just to show the fancy picture for nature nanotechnology. Now, okay, I go to the main discussions. If we can use these kind of breakups in organic semiconductors, apparently not yet, because the organic semiconductor as a thin film it has a very unfavorable materials properties. Most likely, it should be crystalline for higher electronic performance, and hence it's very brittle and it cannot flow. It just melts, and then there's no application, and so it's trapped in a vicious circle of no application. Then nobody really cares to study it, and then there's no new materials properties. So I want to show you one application that I hope that can motivate it. If we really publish that, we can have motivated to get the organic semiconductor out of this trap and have more fundamental study on the mechanical properties of these materials. So I noticed a very unique properties, optical properties of organic semiconductor. On the left-hand side here, you have inorganic semiconductor, and you have the band-like structure. So the absorption coefficient would depend on the wavelength in the way that, okay, at the high wavelength, you have a low absorption. And when you have the photon that with higher energy than the gap, you will actually jump up and you will have a plateau, or you just increase. So basically, you will have the sharp transition of certain wavelength. For example, here for CDT to tellurium, cadmium, you have a very sharp transitions. Whereas in this organic semiconductor, you have a very narrow bandwidth of absorption, and with tunable absorptions. So that is fascinating, because we have to find applications. Because for the semi-transparent organic solar cells, if you have inorganic semiconductor, you cannot do anything other than reduce the thickness of the film. Whereas with organic semiconductors, you can tune the absorptions at the very specific wavelength that you want to. And then if we can apply the meta surfaces, can even enhance higher. So we can harvest higher energy at the large the infrared and let the visible go through. And semi-transparent organic solar cells is the big market right now, because basically green energy buildings will be the norm everywhere. Actually, there are people who trying to do that, but not successfully. So in one paper that I can find, they show some microstructure of the blend polymers with PCBM, traditional solar cell materials. So they shows a tiny peak, 650. So it's still sit on the visible. Recently, there's a new type of solar cells. It's the non-polar solar cell with the absorptions, as shown here by NORA. The NRK really light at the infrared. And then, so I had an idea that if we can engineer the periodic structure of the NFA semiconductors in solar cells, we can even improve the absorptions at this wavelength by, we can show that by first optical simulations and device simulations to show the electronic characterization. Because of lack of time, I just want to show you here the absorptions of enhancement in metal surfaces on NFA organic semiconductor. On so in this structure consists of pillars with 150 nanometer width and with 400 nanometer height and the periodic of 600 nanometer. And you can see that with the thin film, we have this kind of absorption. Now, if we add the nanostructure on top, then we can really enhance the absorptions at, out of the visible without changing the absorption of the visible. And this peak is, as you show on this green curve here, it's come from the interaction between the different pillars inside the structure. So if we zoom in and consider the field of what the fields that look like, you can really see that at the deep here, there is no field added by the nanostructure, whereas at the highest peaks here, the field is extremely strong and localized inside the pillar. So this simulations is one of the motivations. I mean, for my constitute motivations for working more on maybe making of nanostructure organic solar cells. And okay, thank you. And with that, I would like just to conclude here the second steps that I have showed the potential of the non-fluorine acceptor metasurfaces in transparent solar cells. And I will consider other structure if I continue this project. For example, the structures that are more related with the fabrication of etching or hot embossing or even dewiring, and complete the electrical and simulations. And with that, I would like to have the grand conclusions. So in this talk, I showed you that by using the unique properties of organic semiconductors, we can invent a new technique of making transistors, for example, OECT devices. And we can also rely on the selective absorption of NFA to show the potential in transparent solar cells. So that kind of constitutes the motivations for the future work more fundamentally to understand the coupling between the processability and functionalities in organic semiconductor. And with that, hopefully to fulfill the promise of organic semiconductors in future electronics and optoelectronics. And I would like to end with acknowledgement. There are many people that I am very thankful for, actually for helping me and for showing me a lot of stuff that I don't know. I mean, I come from a completely different field. So I would like to thank Professor Tung Nguyen for allowing me to work here, and also for providing guidance along the way, and all the CPOS member, Professor Witzel, for his always very supportive and guidance, and Shantanu, who showed me a lot on microfabrication of stretchable electronics, Professor Leo and Brian's for their passions and for a lot of discussions, and to the group of Professor Kevin Plaxco, Gabi, Alejandro, and Caitlin, Andrea, who left already. And some of the work I showed you previously from the group in EPFL. Tapa, who is the one who did the work on the first author in the breakout study, and many other people. So I would like also to thank the funding agencies from UCSB, the CPOS, the CNSI, and some of my fundings come from the Swiss National Science Foundations. And with that, I would like to end my talk, and I hope that we have some time for discussion. Thank you for your attention. Okay, so as moderator of the CPOS meeting, I see that there is a question. Please feel free to ask question in the chat or just unmute yourself.
There one question in the chat, Tung.
Yes. Okay.
What is the rationale for your choice of 150 nanometer width of the pillars?
Okay. Actually, I take into account many considerations. The structural height and width should not be exceed 400 nanometers because it's the thickest layer of organic solar cells that has been mixed with NFA. As you know, that organic solar cells cannot be very thick because they cannot be made very thick. So I choose the 400 nanometer height as my thickness. Now the width, so I tune the width in a function of the height in order to have this very high thick. So I have a slide showing you actually by tuning the width at different size, we have different resonance. So that would be the highest resonance at infrared, and without altering the absorptions of the thin film. So my rationale is choosing the height first, and because of the limitations of the thickness of an organic semiconductor.
All right. So I have a question regarding of your fabrication method, Tung.
Yes.
Because you try to highlight the advantage over the existing one.
Yes.
So what is the typical time frame that for you to go through all the steps? So that number one, the duration, the time it takes to do that. And the second, that it should be straightforward if one want to do like kind of scale up and multi area, like large areas and that kind of scale up method.
Yes. Thank you, Quinn. It's 2 hours for me to make like 4 wafers. 4 wafers would be 60 devices. So in 2 hours, now let's say the time, accumulated time, because there are some steps like evaporation. If we can do it immediately, it could be quite short. So it could be 2 hours for 160 devices. This is nanofabrication technique, so it can be scaled up. I am also making a new mask to make arrays on a glass wafer of OECT like that. So I think it should be, because it requires less steps, it would be much easier to do than the ones that the Maliaras group and companies are working on at the moment that require additional 2 steps and with some facilities that are not available, widely available.
Right. Thank you. Other question?
Yes. Thank you, Ming, for the comments. So you want to fabricate the resolutions of lithography is 200 nanometer. Oh, okay. I don't know that. So
I
maybe.
have a question too. Oh,
okay.
Yes. Thank you for the nice talk. And my first question is that so what is the maximum resolution you expected? I mean, you show that like you make channel lengths up to 20 micrometer. but for example, can you make like a smaller microchannel such as like you can make under 5 micrometer or something? So
under 5 micrometers, I think theoretically, I am having the mask for that. We can make a channel of 10 micron by 10 microns. So
yes,
I am using the mask, which is printed mask and not chromium mask. So my printed mask has the resolutions warranty at 10 micrometer. So that is their fabrication technique. This mask costs like $70 each, compared to $200 or $250 for the chromium printed mask with the resolution of 2 microns. So in my opinion, it depends on the resolution of the printed mask than the resolution of the fabrication techniques. And I am making the one with 10 by 10 micrometers square.
yes, because I think that if you go to like a small channel length, there I expect that there should be like a problem in delamination of the film or something. So
okay, yes, that's a good point. We will take that into account.
yeah. And my second question is that so you think your new fabrication method can be applied into other various active material? For example, we have PJ2TT like that. So do you have any idea to minimize unexpected side effect? Because we know that sometimes organic solvent affects into the morphology of active material a lot. So
Yep. So the question can be answered by studying the. We have several ways to overcome the problems. So we can choose the photoresist that can be dissolved by a solvent that would not affect the performance of the organic semiconductor. I choose as example the AZ 4100, which is in my hand in the fabrication lab. But in terms of photoresist, there are a lot of choice, and I think there will be some the photoresist that can be dissolved with solvents that are not affected by the that will not affect the organic semiconductor.
Yes, that's good.
Yep. And of course, it depends on what kind of active materials you want to work with, and then we can go back from there.
Thank you.
Hi, this is Fong. Thank you for the talk. I wanted to ask for these, microfabricated OECTs. I think you showed that you apply a gate in like a well with methylene blue for something of this size scale, like 20 nanometers. How would you actually have the complete device if you require this, aqueous layer for gating
this one
transistor? Right.
What you mean? Okay. So actually, because it's an electrolyte, the dip and also very highly the concentrations in PBS of sodium chloride is 100 micromolar, so it's very conductive electrolyte. The distance between the gate and this channel, as I show here, between this part and this part, are not really important actually. The steady state of this device, like when you apply a voltage and this goes to the steady state, is less than 100 microseconds. So if you scan the device with a resolution higher than 100 microseconds, it could not depend on the distance between the gate and the channel. So in this case, in my in this, the distance is like 2 centimeters between this part and this part.
Okay, so I guess like in a use case, like in the brain you showed, you would actually just use like some biological potential to gate the device, and so the distance between the gate and the active material doesn't matter.
It depends on application, but this one I don't think that could not be important. If you want to miniaturize the device, the whole thing, So there's a way, I didn't show here, that we can put the gate just right next to the channel using the fabrication techniques. So instead of having here the two electrodes, we can just put one right there, called planar structure. And because the photoresist will cover the gate anyway, or we can even open it. So if we have one gate at like 10 or 5 microns next to the channel, that would not be a problem. But for these applications, I don't need it, so I don't use it yet. But for sure, for some other applications, maybe we will consider it in the future.
Okay. Thank you.
Thank you for your question.
Any other question for Tung? Okay. If not, thank you, Tung, again for a very excellent talk. And I wish everybody a great rest of the day. Take care.
Yeah, thank you.
And next week we have outside speaker, right?
Yes, next week we
Harold
have.
Ide.
Yes.
All right.
Yep.
Thank you.
Have a nice one, everyone.